The nearest star to Earth is only 4.2 light-years away. That sounds close. Astronomers call it our cosmic neighbour. Science fiction writers treat it as humanity's first stepping stone to the galaxy. But if you actually try to travel there, something terrifying happens. The journey to Proxima Centauri would take our fastest spacecraft over 70,000 years. A radio message sent home would not arrive for more than 4 years. No rescue mission could ever reach you. No supply ship could ever find you. The distance is so vast that the word nearest becomes a lie your intuition tells you to survive the truth. The closest star in the universe is already so far away that the journey to reach it may be fundamentally incompatible with human life as we understand it. If you want to understand why the nearest star is already the most terrifying destination humanity could ever attempt, do me a small favour and hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. Look up at the night sky on a clear evening from anywhere in the southern hemisphere. Find the constellation Centaurus. Somewhere within that ancient pattern of light sits a star so dim that no human eye has ever seen it without a telescope. It glows with barely 5,000ths of 1% of the sun's luminosity. It weighs roughly 12% of the sun's mass. It measures about 15% of the sun's width. If you replaced our sun with this star, the Earth would freeze solid within days. Noon would look like perpetual dusk. The oceans would begin crystallizing before the first week ended. This feeble, sputtering ember of a star is Proxima Centauri, and it holds a title that sounds like an invitation but functions like a trap. It is the nearest star to our solar system, the closest sun beyond our own, the first possible destination for any species that dreams of reaching another star. That title has echoed through decades of astronomy textbooks, science fiction novels, and mission proposals. Nearest. The word lands softly. It suggests proximity. It implies accessibility. It whispers that the first step beyond our solar system might be a step we could actually take. But that whisper is a lie. Not a deliberate lie. Not a conspiracy, something worse. A lie that our own language tells us because our brains evolved to survive on a tiny rock and never developed the wiring to comprehend what 4.24 light-years actually means when you try to cross it. Proxima Centauri was discovered in 1915 by Robert Innes, a Scottish-born astronomer working at the Union Observatory in Johannesburg, South Africa. Innes was comparing photographic plates of the southern sky when he noticed a faint star with an unusually large proper motion, meaning it moved across the sky faster than almost anything else at that distance. That rapid angular motion was the clue. Stars that appear to move quickly against the background are usually nearby, just as a bird flying past your window seems to move faster than an airplane at cruising altitude, even though the airplane is travelling far faster in absolute terms. Innes measured the parallax, the apparent shift in the star's position as Earth orbits the Sun, and confirmed that this dim red dwarf sat closer to our solar system than any other known star. He named it Proxima, from the Latin word for nearest. The name stuck, and for over a century, it has been gently misleading every person who hears it for the first time. Proxima Centauri is not a solitary wanderer. It belongs to a triple star system. The two primary stars, Alpha Centauri A and Alpha Centauri B, form a binary pair that orbits each other roughly every 80 years at a separation similar to the distance between our Sun and Uranus. These two are reasonably Sun-like. Alpha Centauri A is slightly larger, slightly brighter, and slightly hotter than our Sun. Alpha Centauri B is a bit smaller, a bit cooler, and a bit dimmer. Together, they form one of the most studied binary systems in the sky, visible to the naked eye as the third brightest star system from Earth. Proxima Centauri orbits this pair at an enormous distance, roughly 13,000 astronomical units away, where 1 astronomical unit equals the distance from Earth to the Sun. At that separation, Proxima takes approximately 550,000 years to complete a single orbit around its two brighter companions. It is so far from them that for centuries, astronomers debated whether Proxima was gravitationally bound to the Alpha Centauri system at all, or merely passing through the same region of space by coincidence. Modern measurements of its motion confirmed the gravitational link. Proxima is a genuine member of the family, but it orbits at such a staggering distance that the family barely holds together. This dim red dwarf is what astronomers classify as an M-type main sequence star, specifically M5.5v. Red dwarfs are the most common type of star in the Milky Way, accounting for roughly 70% of all stellar objects. They burn hydrogen so slowly and so efficiently that they can sustain fusion for trillions of years. Our Sun will exhaust its fuel in roughly 5 billion years. Proxima Centauri will continue burning for perhaps 4 trillion years. Long after the Sun has swollen into a red giant and collapsed into a white dwarf, long after the Earth has been consumed or flung into darkness, Proxima will still be glowing, faintly, stubbornly, alone with whatever remains of its planetary companions. This extraordinary longevity makes Proxima Centauri scientifically fascinating, but it also makes the star deceptive, because a star that will outlive almost everything else in the galaxy feels permanent, and permanent things feel reachable. They feel patient. They feel like they will wait for us. But Proxima is not waiting. It is sitting at a distance that needs to be converted out of the polite abstraction of light years and into numbers that actually hurt. 1 light year is the distance that light travels in 1 year, moving at approximately 186,000 miles per second. In the vacuum of space, nothing moves faster. Light crosses the distance from Earth to the Moon in about 1.3 seconds. It reaches the Sun in about 8 minutes. It passes Neptune in roughly 4 hours. It exits the solar system's most generous boundary in less than a day. But it takes 4 years, 3 months, and roughly a week to reach Proxima Centauri. 4.2, 4 light years. That number translates to approximately 24.9 trillion miles, or roughly 40.2 trillion kilometers. 24.9 trillion miles. Let that number sit for a moment, because your brain is doing something right now that it does automatically with large figures. It is rounding. It is abstracting. It is filing the number away as very big and moving on. Human cognition developed to process distances measured in footsteps, river crossings, maybe the span of a horizon. It did not evolve to distinguish between 1 trillion and 24 trillion in any visceral way. Both register as absurdly large. Both feel equally unreal. And that flattening of scale is exactly where the lie begins. Because 24.9 trillion miles is not just a big number. It is a number that breaks every analogy you have ever used to make distances feel manageable. Try this. If you could drive a car at 65 miles per hour without stopping, without sleeping, without refueling, just a straight highway stretching from Earth to Proxima Centauri, the trip would take roughly 44 million years. 44 million years at highway speed. When your hypothetical car departed, the Indian subcontinent had not yet finished colliding with Asia to form the Himalayas. The Mediterranean Sea was in the process of drying up entirely in one of the most dramatic geological events in Earth's history. Apes had not yet diverged from monkeys. The entire arc of primate evolution that leads to you standing upright and reading these words would unfold and complete itself before your car reached the nearest star. The engine would need to run for a span of time longer than the existence of the human species multiplied by a factor of 2,000. Or try it from the other direction. If you laid standard United States $1 bills end to end, each bill measuring 6.14 inches long, you would need approximately 257 quadrillion bills to build a chain, reaching from Earth to Proxima Centauri. 257 quadrillion. The total amount of money in circulation on Earth, in all currencies, converted to dollars, is roughly 40 trillion. You would need to multiply every dollar currently in existence by more than 6,000, and still not have enough paper currency to physically bridge the gap to the nearest star. The bills themselves would weigh more than the mass of a significant asteroid, and they would stretch across a void so empty that for the vast majority of the journey, no star, no planet, no rock, no molecule would be close enough to see. This is what 4.24 light years means when you pull it out of an astronomy textbook and try to make it physical. The distance is not large in the way that a mountain is large or an ocean is large. Those are distances human civilizations have crossed. The distance to Proxima Centauri is large in a way that mocks the entire concept of crossing. It is a distance that sits quietly in the language of astronomy, using words like nearest and neighbour and close, while representing a gap so extreme that every vehicle, every road, every bridge, every ship humanity has ever built becomes meaningless noise on the scale required. And here is where the psychology of the word nearest inflicts its deepest damage. When humans hear that Proxima Centauri is the nearest star, they unconsciously perform a comparison. Nearest means closer than the alternatives. It means the best case. It means that whatever difficulty the distance represents, it is the minimum difficulty. And that mental framing creates a ghost of hope, a sense that because Proxima is the nearest, it must be somehow within reach, or at least closer to reach than anything else. But nearest in interstellar terms does not mean what nearest means in any human context. The nearest hospital can save your life because ambulances exist. The nearest airport can connect you to the world because aircraft exist. The nearest star cannot be reached because nothing exists that makes the crossing possible within a human lifetime, using any technology that has been built or funded. The word nearest applies to Proxima Centauri, the way shallowest applies to the deep ocean. The Mariana Trench drops to nearly 36,000 feet below the surface. If someone told you the shallowest point of the abyssal ocean floor was only 12,000 feet down, you might feel briefly comforted. 12,000 feels better than 36,000. But you would still be crushed to death long before you reached it without a vehicle specifically engineered to survive the pressure. The shallowest abyss is still an abyss, and the nearest star is still a star system that sits across a vacuum so wide and so empty that the journey to reach it turns human-scale travel into a rounding error. The cruelty deepens when you learn what sits at the destination, because Proxima Centauri is not just a star, it is a star with planets. And at least one of those planets orbits in the habitable zone. In 2016, astronomers using the European Southern Observatory's HARP spectrograph announced the discovery of Proxima Centauri b. This planet orbits its star every 11.2 Earth days at a distance of approximately 4.5 million miles, over 20 times closer than Earth is to the Sun. But because Proxima Centauri is so much dimmer and cooler than our Sun, this tight orbit places the planet squarely within the habitable zone, the orbital band where surface temperatures could theoretically permit liquid water. Proxima b has an estimated minimum mass of roughly 1.05 Earth masses, making it similar in size and likely composition to our own world. The discovery sent shockwaves through the astronomy community and the public imagination. An Earth-sized planet in the habitable zone of the nearest star. The phrasing alone felt like a cosmic invitation. Here was a world that might, in some configuration of atmosphere and magnetic field and geological luck, harbour conditions friendly to life. And it was right next door, 4.24 light-years away, the nearest possible place where an Earth-like world could exist around another star. But the planet's situation is complicated. Proxima Centauri is a flare star. It is classified as an eruptive variable, meaning it is prone to sudden, violent outbursts of radiation. In 2019, astronomers detected the largest stellar flare ever recorded from Proxima Centauri, a burst that made the star shine 14,000 times brighter than normal in ultraviolet wavelengths. These flares bombard any close-orbiting planet with intense radiation, potentially stripping away atmospheres and sterilizing surfaces. Whether Proxima b retains a meaningful atmosphere remains unknown. Whether liquid water survives under that bombardment remains unknown. Whether the planet is tidally locked, showing the same face to its star at all times, remains likely but unconfirmed. The world might be habitable, or it might be a scorched rock scoured clean by stellar tantrums. The uncertainty itself is part of the torment. There might be somewhere worth going. There might be an Earth-sized world with liquid water and a stable surface and the raw ingredients for biology. And it is right there, at the nearest star, close enough to name, close enough to characterize with the next generation of telescopes, but not close enough to visit. Proxima Centauri does not host just one confirmed planet. In 2022, astronomers announced a candidate planet designated Proxima d, an extraordinarily small world with a minimum mass of roughly 1/4 of Earth's mass, orbiting its star every 5.15 days at a distance of approximately 4 million kilometers. In 2025, the NIRPS instrument, the Near-Infrared Planet Searcher, operating on the European Southern Observatory's Very Large Telescope, independently confirmed Proxima d's existence. This makes Proxima d one of the lightest exoplanets ever confirmed through radial velocity measurements. It orbits far too close to Proxima Centauri to reside in the habitable zone, and its tiny mass suggests it may be a bare rocky body with little to no atmosphere. But its confirmation added another member to the Proxima system, another world circling the nearest star. A third planet, designated Proxima c, was proposed in 2019 based on signals in radial velocity data, suggesting a larger world orbiting much farther out, well beyond the habitable zone, with an estimated minimum mass of roughly 6 Earth masses. If real, it would have been a cold, Neptune-like, or super-Earth-class planet with an orbital period of about 5.2 years. For several years, Proxima c lingered in the literature as a candidate, supported by some analyses and disputed by others. Hubble Space Telescope astrometry seemed to provide supporting evidence, and a tentative direct imaging detection was reported using the SPHERE instrument, though the authors themselves acknowledged the detection was uncertain. Then in 2025, the same NIRPS observations that confirmed Proxima d delivered a blow to Proxima c. The instrument was unable to confirm the radial velocity signal attributed to the planet. Hints of a signal at a similar period remained, but at a lower amplitude than previously claimed, leaving Proxima c's existence inconclusive at best and doubtful at worst. As of now, the Proxima system contains 2 confirmed planets, B and D, and one candidate that may not exist at all. This planetary census matters for the story of the journey, because it defines what the destination looks like. The nearest star is not merely a point of light sitting in the void. It is a system, a small, battered, radiation-scoured system anchored by a dim red dwarf that will outlive nearly everything else in the galaxy. Around it orbits at least one world that might, under the right conditions, be habitable, and another world so small it represents the edge of what our best instruments can detect. The system is real. The planets are confirmed. The habitable zone candidate exists. And all of it sits at a distance so extreme that the confirmation of these worlds does not bring them closer. It only makes the gap feel more painful. There is a particular kind of cruelty in knowing exactly what you cannot reach. A prisoner who has never seen the outside world suffers differently from a prisoner who can see a sunlit garden through a barred window. Proxima Centauri b is the garden. The bars are 24.9 trillion miles of vacuum, and the window is every telescope and spectrograph that confirms, with increasing precision, that the nearest potentially habitable world is right there, orbiting the nearest star, separated from us by a distance that turns right there into one of the most misleading phrases in the history of human language. The astronomers who study Proxima Centauri are not being cruel on purpose. They are doing extraordinary science. The NIRPS observations that confirmed Proxima d achieved radial velocity precision measured in tens of centimeters per second, detecting the gravitational wobble of a planet lighter than Mars, tugging on a star 4.24 light-years away. The espresso spectrograph refined the mass of Proxima b to remarkable accuracy. Future observatories, including the extremely large telescope now under construction in Chile, may eventually characterize Proxima b's atmosphere, searching for biosignatures, chemical fingerprints of life, in the light reflected from or filtered through that distant world's sky. We may one day know whether Proxima b has oxygen, whether it has methane, whether its atmospheric chemistry betrays the presence of biology. we may confirm that life exists at the nearest star. And we will know all of this from Earth, through light, through instruments, through data traveling at the speed of electromagnetic radiation across 4.24 years of void. We will know it the way a person knows what a photograph shows. We will see it. We will analyze it. We will publish papers about it. And we will not be there. Everything you have heard so far describes only the first layer of the problem. The distance, the scale, the raw physical gap between here and the nearest star. This is the foundation on which everything else rests, and it is already shattering. But distance alone does not make the journey terrifying. Distance is a number. Numbers can be divided. Gaps can, in principle, be crossed. What transforms the distance from a challenge into a crisis is what happens when you try to divide it by speed. When you take this unfathomable gap and ask the only question that matters for anyone who dreams of reaching another star, how long would the crossing actually take? The answer turns everything darker. In 1977, humanity launched the fastest objects it had ever sent beyond the gravitational grip of the Sun. Two identical spacecraft, Voyager 1 and Voyager 2, departed Earth on trajectories that would carry them past Jupiter, past Saturn, and eventually out of the solar system entirely. Voyager 1 is now the most distant human-made object in existence. As of 2026, it sits approximately 173 astronomical units from the Sun, where 1 astronomical unit equals the 93 million mile distance from Earth to the Sun. That means Voyager 1 has travelled roughly 16 billion miles since Richard Nixon was president. It flies at approximately 17 kilometers per second relative to the Sun, 38,000 miles per hour, 61,000 kilometers per hour. That velocity is fast enough to cross the entire continental United States in about 5 minutes. It is fast enough to circle Earth's equator in under 40 minutes. It is a speed so far beyond everyday human experience that it feels like it should matter on interstellar scales. It does not. In late 2026, Voyager 1 is projected to reach a milestone that NASA and the Jet Propulsion Laboratory have been quietly tracking for years. It will become the first human-made object to travel 1 full light day from Earth. A light day is the distance light crosses in 24 hours, roughly 16 billion miles, or 25.9 billion kilometers. That number sounds spectacular, and it is. No human artifact has ever been this far from its origin, but consider what the milestone actually demonstrates. Voyager 1 has been flying for nearly 50 years, continuously, without stopping, at 38,000 miles per hour, and it has covered 1 light day. Proxima Centauri is not 1 light day away. It is approximately 1,549 light days away. Voyager 1 would need to repeat its entire 50-year journey more than 1,500 times, back to back, to close the distance to the nearest star. At its current velocity, the math is unambiguous. Voyager 1 would require over 73,000 years to reach Proxima Centauri. To place that in human terms, 73,000 years ago, anatomically modern humans shared the planet with Neanderthals. The last ice age had not yet reached its peak. Agriculture did not exist. Writing did not exist. The concept of a city did not exist. Every civilization that has ever risen and fallen on Earth, every empire, every revolution, every technological leap from the wheel to the microprocessor fits comfortably inside the last 10,000 years. Voyager 1 would need 7 times that span to reach the nearest star. The entirety of what we call human history is a rounding error on the journey time. And Voyager 1 is not even the fastest object humanity has launched on an escape trajectory from the solar system. New Horizons, which flew past Pluto in 2015, was the fastest spacecraft ever launched directly from Earth, departing at roughly 16.3 kilometers per second. After a gravity assist from Jupiter, it settled into an outward trajectory that will carry it beyond the solar system. But it is actually slower than Voyager 1 at comparable distances, because Voyager received gravity assists from both Jupiter and Saturn. At 100 astronomical units, New Horizons will be traveling at approximately 13 kilometers per second, around 4 kilometers per second slower than Voyager 1. Even if New Horizons were somehow aimed directly at Proxima Centauri at its launch velocity, the crossing would take roughly 78,000 years. Faster launch, similar agony. The natural question becomes, what about our absolute fastest spacecraft? The Parker Solar Probe, launched in 2018 on a mission to study the Sun's corona, holds the record for the fastest object ever built by human hands. During its closest approach to the Sun on December 24, 2024, Parker reached a staggering 191 kilometers per second. That translates to approximately 430,000 miles per hour. At that velocity, you could fly from New York to Los Angeles in under 20 seconds. You could reach the moon in roughly 33 minutes. It is a speed that makes Voyager 1 look stationary, but context matters enormously here. Parker Solar Probe achieves this velocity only at perihelion, its closest approach to the Sun, where it dives deep into the Sun's gravitational well and picks up tremendous speed. It is not travelling outward from the solar system. It is in a tight elliptical solar orbit, racing around the Sun and then slowing dramatically as it swings back outward. Parker's speed is the product of falling toward the Sun, not escaping from it. The energy required to maintain that velocity on a straight line away from the Sun and out of the solar system would be vastly greater than anything Parker carries. But set that aside. Indulge the hypothetical. Imagine you could somehow sustain Parker Solar Probe's peak speed of 191 kilometers per second on a direct course to Proxima Centauri. The distance is approximately 4.02 times 10 to the 13th kilometers. At 191 kilometers per second, the journey would take roughly 6,600 years, faster than Voyager by a factor of 11, still measured in millennia, still longer than the entire span from the construction of the Great Pyramid of Giza to the present day, nearly half as long again. The fastest thing humanity has ever built, sustaining its absolute peak velocity in a direction it was never designed to travel, arrives at the nearest star in a time frame that makes human civilization look like a footnote. This is the speed problem, and it does not care about incremental improvements. Consider the propulsion technologies that engineers and physicists have proposed for deep space missions beyond conventional chemical rockets. Nuclear thermal propulsion, in which a nuclear reactor heats propellant to extreme temperatures and expels it for thrust, has been studied since the 1960s under programs like NERVA. The best nuclear thermal designs might achieve exhaust velocities roughly twice those of the most efficient chemical rockets, potentially allowing spacecraft to reach speeds of perhaps 30 to 50 kilometers per second with optimal staging. That reduces the Proxima Centauri journey from 73,000 years to perhaps 25,000 to 40,000 years, an improvement. But still a sentence measured in geological epochs. Nuclear electric propulsion, which uses a nuclear reactor to power ion drives that accelerate charged particles to very high exhaust velocities, offers better theoretical performance. Ion drives produce tiny amounts of thrust but can maintain it for months or years, slowly building velocity over time. The Dawn spacecraft used ion propulsion to explore the asteroid belt. Current ion drives achieve exhaust velocities around 30 to 50 kilometers per second, and advanced designs might push that to 100 or even 200 kilometers per second. If a nuclear electric spacecraft could accelerate continuously for years, it might reach cruise velocities of 100 to several hundred kilometers per second. At 200 kilometers per second, the trip to Proxima Centauri shortens to roughly 6,300 years. At 500 kilometers per second, an extremely optimistic figure requiring propulsion systems that do not yet exist, the journey drops to approximately 2,500 years, still longer than the gap between the Roman Republic and the present day. The pattern is relentless. Double the speed, halve the time, and the time is still inhuman. Quadruple the speed, quarter the time, and the time is still measured in millennia. No extrapolation of existing chemical, nuclear thermal, or nuclear electric propulsion reduces the journey to Proxima Centauri to anything shorter than many centuries. These technologies are not failures. They are triumphs of engineering that have transformed our ability to explore the solar system. They are simply irrelevant to interstellar distances. The gap between what they can do and what interstellar travel demands is not a gap that better engineering can close. It is a gap that requires a fundamentally different category of propulsion, which brings us to the most ambitious interstellar concept ever funded: Breakthrough Starshot. In April 2016, physicist and venture capitalist Yuri Milner stood on a stage in New York City alongside cosmologist Stephen Hawking and announced a $100 million research program aimed at something that had never been seriously funded before: sending a spacecraft to another star within a generation. The concept was audacious. Build a ground-based laser array capable of producing 100 gigawatts of coherent light. Use that array to accelerate tiny spacecraft, each weighing only a few grams and attached to ultra-thin reflective sails roughly 4 meters across, to 20% of the speed of light. At that velocity, approximately 60,000 kilometers per second, a probe would reach Proxima Centauri in roughly 20 years. Add 4.24 years for the return data transmission at light speed, and the total mission time from launch to first results would be about 24 years. Within a human career, within a single generation, the announcement generated enormous excitement. Here was a credible, funded, scientifically backed proposal to reach the nearest star in a time frame that humans could actually experience. The board included Hawking and Facebook co-founder Mark Zuckerberg. The advisory committee was chaired by Harvard professor Avi Loeb. Serious researchers from serious institutions were involved. The engineering challenges, however, were equally serious. Building a laser array that combines thousands of individual lasers into a single coherent beam of 100 gigawatts, a power output comparable to the total electricity consumption of a mid-sized country, requires advances in photonics, beam combining, and atmospheric compensation that do not currently exist. The sails must be fabricated from materials that can reflect the laser light efficiently enough to accelerate without being destroyed by the beam's intensity. The probes themselves must carry cameras, communication systems, navigation instruments, and power sources, all within a mass budget of a few grams. Each probe must survive acceleration forces on the order of 10,000 times Earth's gravity during the roughly 10-minute boost phase. Once at cruise velocity, the probes must endure 2 decades of transit through the interstellar medium, where even individual hydrogen atoms and microscopic dust grains become projectiles, impacting at 20% of light speed. At that velocity, a grain of dust weighing a microgram delivers the kinetic energy equivalent of several sticks of dynamite detonating on the hull. Over 20 years and 4 light-years of sparse but not perfectly empty space, cumulative damage from interstellar medium impacts becomes a genuine mission risk. And then there is the communication problem. A gram-scale probe at Proxima Centauri must transmit data back to Earth across a distance of 4.24 light-years, using a laser or radio system constrained by the mass and power budget of a device smaller than a smartphone. Recent analyses from researchers associated with the project estimate that data rates on the order of roughly 1 kilobit per second might be achievable using onboard laser communications and a large receiving array on Earth, yielding a data return of a few gigabytes per year. That is comparable to what New Horizons transmitted after its Pluto flyby. Enough for images and basic scientific data. But achieving even that modest rate requires extraordinary precision in pointing a communications laser from a chip-sized spacecraft across interstellar distances, hitting a receiving station that, from the probe's perspective, is an invisible speck lost in the glare of the sun. For roughly 9 years, Breakthrough Starshot funded studies, convened scientific meetings, and made incremental progress on specific technical challenges. Researchers demonstrated coherent beam combining with tens of lasers in laboratory settings. Caltech scientists performed the first direct radiation pressure measurements on miniature light sail membranes, a foundational experimental step published in early 2025. Prototype Sprite spacecraft, Tiny centimeter-scale circuit boards representing precursors to the envisioned Starship probes were launched to orbit and successfully operated. Advances in light sail materials, optical lithography techniques, and beta-voltaic nuclear batteries for onboard power were investigated. But in September 2025, Scientific American reported that Breakthrough Starshot was on indefinite hold. Philip Lubin, one of the project's lead researchers at the University of California, Santa Barbara, estimated that the program had spent roughly $4.5 million of its proposed $100 million budget across approximately 30 research contracts. Activity had peaked in the first 4 to 5 years and then quietly declined. Meetings ceased, communications went silent. No formal cancellation was announced, but no continuation was evident either. The project's executive director and advisory chair declined interviews. A promised comprehensive report on the project's status had not appeared by the time the article went to print. As of early 2026, the future of Breakthrough Starshot remains murky. Analyses from researchers involved with the project describe it as a success in terms of advancing the science of interstellar propulsion and normalizing interstellar travel as a serious engineering goal. But the hardware required for an actual mission, the 100-gigawatt laser array, the flawless light sails, the gram-scale probes capable of surviving relativistic flight and transmitting data across light years, remains decades away at best. The total mission cost, initially estimated by Milner at $5 to $10 billion, would likely be far higher. Here is what Breakthrough Starshot reveals about the speed problem, even in its most optimistic form. The most ambitious interstellar mission ever funded, backed by a billionaire, advised by some of the world's leading physicists and engineers, targeting only a gram-scale robotic flyby with no deceleration and no return, struggled to clear the first engineering hurdles with $100 million over nearly a decade. The concept remains theoretically viable. The physics does not forbid it, but the gap between theoretical viability and actual hardware is vast, and the timeline for closing that gap stretches well beyond the near future. 20% of light speed is not something humanity can achieve today. It is something humanity might achieve in several decades if the funding, political will, and engineering breakthroughs all converge. And even then, the result is a flyby. A fleet of tiny chips screaming past Proxima Centauri at 60,000 kilometers per second, gathering a few hours of close-range data before continuing into the void forever. No orbit, no landing, no return. A brief glimpse purchased with decades of development and billions of dollars. Now, set aside probes entirely. Forget chips and light sails and laser arrays. Ask the question that science fiction has trained us to ask, and that physics refuses to answer gently. What about sending people? A crewed mission to Proxima Centauri is a fundamentally different problem from a robotic flyby. Not a harder version of the same problem. A different problem. A probe can be tiny. A crewed vessel must be enormous. It must carry human beings, which means it must carry atmosphere, water, food, medical supplies, radiation shielding, exercise facilities, waste processing systems, redundant life support, and enough spare parts to maintain all of these systems for the duration of the journey. It must carry propulsion systems massive enough to accelerate this entire payload to interstellar cruise velocity and then decelerate it upon arrival, because humans cannot survive a flyby at 20% of light speed. They need to stop. Stopping requires carrying roughly as much fuel as accelerating, which doubles the mass, which requires more fuel to accelerate the extra mass, which increases the total mass further in a cascading cycle that rocket engineers call the tyranny of the rocket equation. The deceleration problem alone transforms the mission architecture beyond recognition. A robotic flyby probe can accelerate to cruise speed and never slow down. It screams past the target, gathers what data it can in a few hours, and continues into the void. A crewed vessel cannot do this. The crew needs to arrive at Proxima Centauri with enough residual velocity to enter orbit, or at least a controlled trajectory toward a planetary destination. That means the ship must carry enough fuel to perform a braking burn that reduces its velocity from interstellar cruise speed to near zero. The fuel required for that deceleration burn is roughly equal to the fuel required for the initial acceleration. But carrying that deceleration fuel means the ship is heavier at launch, which means the initial acceleration burn must push more mass, which requires even more fuel. The rocket equation turns this into an exponential spiral. For chemical rockets, the mass ratio becomes absurd within a few kilometers per second of velocity change. For nuclear or fusion drives with higher exhaust velocities, the ratios improve but remain punishing. A ship that needs to accelerate to 5% of light speed and then decelerate back to zero requires a mass ratio that, depending on the propulsion system, could mean the fuel outweighs the payload by factors of dozens or hundreds. The ship becomes mostly fuel. The habitable section, the life support, the crew, the scientific instruments, all of it shrinks to a fraction of the total vessel mass. A tiny kernel of human purpose buried inside a mountain of propellant. To understand what that spiral actually produces, walk through the mass budget of a single concrete mission profile. Imagine a crew of 50 people traveling to Proxima Centauri at 5% of the speed of light, roughly 15,000 kilometers per second, using an advanced fusion drive with an exhaust velocity of 5,000 kilometers per second, far beyond anything that currently exists, but within the theoretical limits of deuterium-helium-3 fusion. The journey takes approximately 84 years. The crew needs a habitat. Start with the habitat module. 50 people require living quarters, communal areas, exercise facilities, medical bays, laboratories, food production, water recycling, atmospheric processing, waste management, power generation, and enough structural volume for psychological health over decades. Based on estimates from long-duration spaceflight research, a minimum of roughly 1,000 cubic meters of pressurized volume per person is needed for a mission of this duration. That is 50,000 cubic meters of pressurized habitat. The structural mass for this habitat, including pressure vessels, internal walls, flooring, equipment mounts, and all the mechanical and electrical systems integrated into the structure, comes to roughly 5,000 metric tons. That is the bare skeleton of the living space, before you add anything inside it. Now add life support, atmospheric processing systems, water recycling plants, hydroponic food production modules, waste treatment systems, thermal regulation equipment, and backup units for all of the above. The International Space Station's life support system masses roughly 20 metric tons and supports 6 people for 6-month increments with regular resupply. A system that supports 50 people for 84 years with zero resupply must be radically more capable, more redundant, and more massive. Estimates place this at roughly 3,000 to 5,000 metric tons, depending on how much food production is handled by onboard agriculture versus stored provisions. Add radiation shielding. The habitat must be surrounded by several meters of hydrogen-rich material to reduce galactic cosmic ray exposure to survivable levels over an 84-year transit. Water is the most practical shielding material because it doubles as a consumable resource. Encasing a 50,000 cubic meter habitat in a water shield, 3 meters thick on all sides, adds roughly 150,000 metric tons of water. The shielding alone outweighs the habitat structure by a factor of 30, but without it, the crew accumulates lethal radiation exposure within a decade or two. Add spare parts, manufacturing equipment, raw materials for onboard fabrication, medical supplies for 84 years, seed stocks for food production, tools, scientific instruments, communication equipment, and the countless other consumables and contingency stores required for a self-sustaining community that can never be resupplied. A conservative estimate places this at 5,000 to 10,000 metric tons. The payload, the total mass of everything that is not propellant, now sits at roughly 165,000 to 170,000 metric tons. Call it 170,000 metric tons for round numbers. This is the mass the propulsion system must accelerate to 5% of light speed and then decelerate back to zero at the destination. Now apply the rocket equation. The Tsiolkovsky rocket equation states that the ratio of initial mass to final mass equals e raised to the power of the velocity change divided by the exhaust velocity. For a mission that must accelerate to 15,000 kilometers per second and then decelerate back to zero, the total velocity change is 30,000 kilometers per second. With an exhaust velocity of 5,000 kilometers per second, the mass ratio is e to the sixth power, which equals approximately 403. That means for every metric ton of payload that arrives at Proxima Centauri, the ship must start with 403 metric tons at departure. Multiply the 170,000 metric ton payload by 403. The total departure mass is approximately 68.5 million metric tons. 68.5 million metric tons. That is roughly the mass of a small metallic asteroid. Most of that mass, over 99.7% of it, is fusion fuel. The habitat, the crew, the shielding, the life support, everything that makes the mission human, accounts for less than 0.25% of the vessel's launch mass. The ship is not a spacecraft with a fuel tank. It is a fuel tank with a spacecraft somewhere inside it, and this estimate assumes a fusion drive with an exhaust velocity of 5,000 kilometers per second, a technology that does not exist. If the exhaust velocity is lower, say 1,000 kilometers per second, which is closer to what near-term advanced propulsion might achieve, the mass ratio explodes to e to the 30th power. That number is so large it becomes physically meaningless. No amount of fuel in the solar system would suffice. The mission becomes not merely difficult but mathematically impossible without propulsion performance that remains firmly in the domain of theoretical physics. This is what the rocket equation does to crewed interstellar travel. It transforms an 84-year journey for 50 people into a 68 million metric ton engineering project. And that is the optimistic version using propulsion technology that has not been invented. The vessel would need to be assembled in space over decades. The fuel would need to be manufactured, likely by mining helium-3 from the lunar surface or the atmospheres of gas giants, an industrial undertaking that dwarfs anything humanity has ever attempted. The cost, measured in current economic terms, would likely exceed the gross domestic product of the entire planet for multiple years. And at the end of all that effort, the result is a ship that crawls to the nearest star at 5% of light speed, taking 84 years to arrive, carrying a crew that will mostly die in transit. The habitable section itself presents challenges without parallel in human engineering. On the International Space Station, roughly 400 cubic meters of pressurized volume supports a crew of 6 for missions lasting 6 months. The station is resupplied every few weeks by cargo vehicles from Earth. Food, water, spare parts, experimental equipment, fresh clothing, even the occasional treat arrive regularly from the surface. Waste is removed, air is partially recycled but supplemented. Water is recycled but not perfectly. The station depends on Earth the way a scuba diver depends on the surface. The tether is long but unbroken. A crewed interstellar vessel cannot be resupplied. Everything the crew will eat for the next 40, 60, or 100 years must either be aboard at departure or grown during the journey. Closed-loop life support, in which air, water and nutrients are recycled with near-perfect efficiency, has never been achieved at the scale or duration required. The most ambitious closed ecosystem experiment in history, Biosphere 2 in Arizona, attempted to sustain 8 people in a sealed 3-acre habitat for 2 years, starting in 1991. It failed. Oxygen levels dropped dangerously, carbon dioxide spiked, crops underperformed, insect pollinators died. The experiment required 2 emergency injections of oxygen from outside. 2 years, 8 people, 3 acres of carefully designed biome, and the system could not sustain itself without external intervention. An interstellar vessel must do what Biosphere 2 could not, at a smaller scale, for a longer duration, in an environment where external intervention is physically impossible. The habitat must also provide enough space for psychological health across decades. Research from submarine operations Antarctic winter-over stations, and long-duration spaceflight consistently shows that confinement in small spaces degrades cognitive function, increases interpersonal conflict, and erodes motivation. The minimum viable habitat for a multi-decade crewed mission is not a capsule, it is a small town. Exercise facilities, medical bays, laboratories, recreation areas, private quarters, food production modules, water processing plants, waste recycling systems, power generation and storage, communication equipment, navigation and propulsion control, and enough structural redundancy that the loss of any single module does not kill everyone aboard. Estimates for the minimum pressurized volume for a crew of 50 on a multi-decade mission range from tens of thousands to hundreds of thousands of cubic meters. The structural mass alone, before adding life support equipment, propellant, shielding, and consumables, would reach thousands of metric tons. The total vessel mass for even a modest crewed interstellar mission climbs into the tens of thousands or hundreds of thousands of metric tons for the payload alone, and into the tens of millions of metric tons once the rocket equation finishes multiplying the fuel requirements. Even the most optimistic designs for crewed interstellar vehicles envision vessels of extraordinary scale. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, designed an uncrewed fusion-powered probe that would reach Barnard's star in roughly 50 years at 12% of light speed. The vehicle itself would have weighed over 50,000 metric tons, most of which was fuel in the form of deuterium and helium-3 pellets, and Daedalus was not designed to carry people or to slow down. It was a flyby probe, just a much larger one than Breakthrough Starshot envisions. Scaling Daedalus to include a habitable section, deceleration capability, and life support for even a small crew would multiply the mass by orders of magnitude. Project Longshot, a study conducted at the United States Naval Academy in the late 1980s, proposed a smaller fusion-powered probe to Alpha Centauri that would take roughly 100 years to arrive. Again, uncrewed. Again, no deceleration to orbit. The engineering challenges for even these stripped-down robotic concepts remain far beyond current capabilities. Controlled fusion propulsion, the engine at the heart of both designs, has not been achieved in any practical form despite decades of research and billions of dollars of investment. The International Thermonuclear Experimental Reactor, ITER, currently under construction in France, aims to demonstrate sustained fusion power, but is not expected to produce net energy until the 2030s at the earliest, and the leap from a ground-based fusion reactor to a spaceflight-rated fusion engine is enormous. If controlled fusion propulsion was somehow mastered and miniaturized for spaceflight, the most optimistic crewed mission profiles suggest cruise velocities of perhaps 5 to 10% of the speed of light. At 10% of light speed, the journey to Proxima Centauri takes roughly 42 years. At 5%, it takes 84 years. These numbers are finally within the span of a human lifetime, at least theoretically. But they require technologies that do not exist, fuel sources that have not been developed in usable quantities, and engineering solutions to problems that have not been solved. They require building the largest, most complex, most reliable machine in human history, and operating it flawlessly for decades in an environment where a single critical failure means the death of everyone aboard, with no possibility of rescue, repair, or resupply from Earth. And even these optimistic timelines assume the ship reaches its target speed almost immediately. In reality, acceleration would take weeks, months, or years depending on the propulsion system and the thrust it produces. Deceleration would take equally long. The cruise phase would be the majority of the journey, but the acceleration and deceleration phases add significant time and fuel requirements. A more realistic mission profile for a crewed fusion-powered vessel might extend the total journey to 60, 80, or over 100 years, even at velocities approaching 5 to 10% of light speed. 100 years in a sealed vessel crossing the void between stars. The people who launch would not be the people who arrive. Their children might not be the people who arrive. This is no longer a mission in any recognizable sense of the word. It is a sentence, a commitment that spans generations. It asks human beings to board a ship knowing they will die in transit, knowing their children will be born, raised, and will die inside its corridors, knowing that only some future generation, people who never chose this journey and never knew the Earth their ancestors left behind, might walk on the surface of another world. The vessel does not merely cross a distance, it becomes a world unto itself, a closed ecosystem, a society, a civilization in miniature, hurtling through emptiness for longer than most nations on Earth have existed. This is what the speed problem ultimately means. It is not simply that humanity cannot go fast enough. It is that the speed required to make the journey bearable by human standards demands propulsion systems that have not been invented, energy sources that have not been harnessed, and engineering reliability that has not been demonstrated over the necessary timescales. Every plausible technology produces a journey measured in decades, at the extreme minimum and millennia, at the realistic maximum. And the shorter the journey time, the more extreme the engineering, the more massive the vessel, the more catastrophic the consequences of failure. The speed problem is not a problem that will be solved by building a slightly better engine. It is a problem that reveals the fundamental mismatch between the distances the universe imposes and the timescales human biology and human engineering can tolerate. Voyager 1 will fly for 73,000 years and still not arrive. Parker Solar Probe at its peak would need 66 centuries. The best nuclear concepts cut the journey to thousands of years. Fusion propulsion, if it ever works, might reduce it to decades, but only for machines, and only at the cost of building something unprecedented in human history. For a crewed vessel, the cost is a 68 million metric ton machine that is 99% fuel, carrying a pocket of human life smaller than a city block, crawling through darkness for the better part of a century. And yet the speed problem, as severe as it is, describes only part of the burden. Because even if you solve it, even if you build the engine, fuel the ship, accelerate to 10% of light speed, and point the vessel toward Proxima Centauri, you have only addressed how long the journey takes. You have not addressed what the journey does to the people inside the ship. You have not addressed what happens when something breaks and no one can help. You have not addressed what it means to send a message home and wait nearly a decade for the answer. You have not addressed what the void itself, the empty, silent, lightless space between stars, does to human minds confined within a metal shell for a lifetime. The distance is the foundation, the speed is the sentence. But the true cruelty of the journey to Proxima Centauri lives in what comes next. On the International Space Station, astronauts live and work approximately 250 miles above Earth's surface. If something goes catastrophically wrong, if a micrometeorite punctures the hull, if a fire erupts in a module, if a crew member suffers a medical emergency, the response time is measured in hours. A Soyuz or Crew Dragon capsule is always docked and ready. From the moment a decision is made to evacuate, the crew can be back on Earth's surface in under 4 hours. Depending on orbital positioning, an emergency landing can happen in as little as 90 minutes. The ground is right there, visible through every window, close enough that astronauts report being able to distinguish individual cities at night, close enough that the curvature of the horizon feels like a gentle reminder rather than a barrier. This proximity is not incidental to the International Space Station's success. It is foundational. Every system aboard that station, every redundancy, every emergency protocol, every psychological support structure depends on the simple fact that Earth is minutes away. Help is real, return is possible, home is visible. Now move outward. On a mission to the Moon, the communication delay is roughly 1.3 seconds each way. You speak, and 2.6 seconds later, you hear the reply. Noticeable but manageable. Apollo astronauts conducted real-time conversations with Houston, the delay creating only a slight awkwardness. Emergency return from the Moon takes approximately 3 days. Not instant, not comfortable, but survivable, plannable, and demonstrated. Move farther. Mars sits between 4 and 24 minutes away by light, depending on orbital positions. A round-trip conversation takes between 8 and 48 minutes. Real-time dialogue is impossible. Every exchange becomes a series of monologues separated by long silences. Mission planners for future crewed Mars missions have grappled with the psychological effects of this delay, understanding that it fundamentally changes the relationship between crew and ground control. An astronaut on Mars who encounters an emergency must make decisions alone, acting on local knowledge, waiting minutes or tens of minutes for any guidance from Earth. Help can eventually arrive, resupply missions could be launched, evacuation vehicles could be pre-positioned, but nothing happens quickly. Mars is the first destination where the tether to Earth begins stretching toward its breaking point. At Proxima Centauri, the tether snaps completely. A radio signal or laser pulse traveling at the speed of light from Proxima Centauri to Earth takes 4 years, 3 months, and approximately 1 week to arrive. 4.24 years, one direction. A round-trip message, sending a question and receiving an answer, requires 8.48 years. Think about what that means in human terms. If a crew at Proxima Centauri sends a transmission saying, "We have arrived safely," the people who receive that message on Earth will hear it in a world that has changed profoundly since the message was sent. Governments will have turned over. Technologies will have advanced. Children born on the day the message was transmitted will be entering 3rd grade by the time it arrives. The crew's families will have aged. Some will have died. The news contained in the reply, when it finally comes back another 4.24 years later, will describe an Earth that is nearly a decade removed from the moment the crew first spoke. Every conversation is a time capsule opened years too late. This is not a communication inconvenience, it is a severing. On the International Space Station, an astronaut can call home and hear a child's voice in real time. On Mars, a message can be sent and a reply received within the same day, or at worst, within the same week. At Proxima Centauri, a parent aboard the ship could send a birthday greeting to a child on Earth and receive the child's response when that child is 8 years older. The rhythm of human relationship, the call and response of conversation, the immediate emotional feedback that allows people to feel connected, all of it dissolves across 4.24 light years. What remains is correspondence. Letters sent into a void, answered by strangers who share your memories but no longer share your present. And this delay is not merely emotional, it is operational. If the crew encounters a system failure they cannot diagnose, they can transmit the data to Earth and wait. Ground engineers, the best in the world, will analyze it, develop solutions, and transmit instructions back. The crew will receive those instructions 8.48 years after the problem occurred. If the problem was urgent, if it involved life support, propulsion, power generation, or hull integrity, 8.48 years of waiting is not a delay. It is a death sentence politely delivered. The crew must solve every crisis with only the people, tools, spare parts, and knowledge aboard. Mission control becomes a historical archive, a source of commentary on events that have long since resolved themselves one way or another. The ground team cannot guide. It cannot intervene. It cannot send anything physical. It can only watch, years after the fact, and hope. This operational isolation transforms the mission into something without precedent in the history of human exploration. Every previous expedition, from Magellan's circumnavigation to the Apollo lunar landings, maintained some form of connection to the civilization that launched it. Magellan's ships could encounter other vessels, resupply at ports, receive news from passing traders. Apollo astronauts were in constant radio contact with Houston. Even the most remote Antarctic research stations receive supply flights and maintain satellite communications. No human venture has ever operated in true isolation, genuinely beyond the reach of help, for years at a stretch. An interstellar crew would be the first humans in history for whom the word alone is not a feeling but a physical fact. Not alone in the sense of being far from friends. Alone in the sense that no other human being in the universe can reach them, help them, resupply them, rescue them, or even speak to them in real time. The nearest other humans would be light years away, separated by a gulf that no ship, no signal, no force of will can bridge within a meaningful time frame. The impossibility of rescue deserves its own reckoning because it represents a psychological boundary that humans have never crossed. On every dangerous expedition in history, there has been at least a theoretical possibility of rescue. Shackleton's crew, stranded on the Antarctic ice after the Endurance was crushed, survived in part because Shackleton could sail a lifeboat to South Georgia Island and summon help. Even in the worst maritime disasters, passing ships might spot survivors. Even on the most remote mountain, a helicopter might arrive. This possibility, however slim, changes how humans experience danger. It allows hope to function. It provides a cognitive anchor. If everything goes wrong, someone might come. At Proxima Centauri, no one is coming. If the crew sends a distress signal the moment they arrive, the fastest conceivable rescue vessel, using technology that does not exist, would require decades to reach them. By the time help arrived, the original crew would likely be dead of old age, even if the initial emergency had not killed them. Rescue is not merely unlikely. It is excluded by physics. The speed of light imposes a minimum response time measured in years, and the speed of any physical rescue vessel imposes a response time measured in lifetimes. The crew does not operate in a high-risk environment with limited rescue options. They operate in an environment where the concept of rescue has no meaning. This reality reshapes every engineering decision. On Earth-orbiting missions, systems are designed with the knowledge that failure can be survived through evacuation. On an interstellar mission, every system must be designed with the knowledge that failure means death unless the crew can fix it themselves. Redundancy must be absolute. Spare parts must be comprehensive. The crew must be trained not as specialists supported by ground teams, but as a self-sufficient civilization capable of manufacturing, repairing, diagnosing, and improvising solutions to problems that no one predicted, using only the materials they carried at departure. This is an engineering philosophy fundamentally different from anything humanity has practiced in spaceflight. It is closer to the challenge of building a self-sustaining colony than to the challenge of operating a spacecraft. And it must function perfectly for decades in the most hostile environment imaginable. That environment begins the moment the ship leaves the protective cocoon of the heliosphere. Our sun generates a constant outflow of charged particles called the solar wind, which inflates a vast bubble around the solar system known as the heliosphere. Inside this bubble, the solar wind's magnetic field deflects a significant fraction of incoming galactic cosmic rays, the high-energy particles that permeate interstellar space. The heliosphere is not a perfect shield. Cosmic rays still penetrate it, and astronauts aboard the International Space Station receive measurably higher radiation doses than people on Earth's surface. But the heliosphere provides a meaningful reduction in cosmic ray flux, especially for the most energetic and damaging particles. Beyond the heliosphere, that protection vanishes. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, in August 2012, approximately 122 astronomical units from the Sun. Its instruments immediately detected a sharp increase in cosmic ray intensity. The interstellar medium is bathed in galactic cosmic rays, particles accelerated to enormous energies by supernova remnants, neutron stars, and other violent astrophysical processes throughout the Milky Way. These particles include protons, helium nuclei, and heavier ions traveling at significant fractions of the speed of light. When they strike biological tissue, they can shatter DNA strands, cause mutations, damage cellular repair mechanisms, and over time, significantly increase cancer risk, neurological degradation, and other radiation-related pathologies. The biological damage from galactic cosmic rays is qualitatively different from the radiation hazards humans face on Earth or even in low Earth orbit. On Earth's surface, the atmosphere and magnetosphere block almost all cosmic ray particles before they reach ground level. In low Earth orbit, the magnetosphere still provides partial protection. Beyond the heliosphere, there is nothing between the crew and the full flux of galactic cosmic radiation. The most dangerous component consists of heavy ions, atomic nuclei of elements like iron and silicon, stripped of their electrons and accelerated to near light speed. When one of these heavy ions passes through living tissue, it does not merely deposit energy along a narrow track the way a medical X-ray does. It creates a column of severe damage through every cell it crosses, shattering molecular bonds, producing cascades of reactive chemical fragments, and leaving a trail of cellular destruction that the body's repair mechanisms struggle to address. A single heavy ion traversal through a cell nucleus can cause complex DNA damage at multiple sites simultaneously, the kind of damage that is most likely to result in permanent mutation or cell death rather than clean repair. Over the course of a multi-decade journey, every cell in every crew member's body would be traversed by heavy ions multiple times. The cumulative effect is not a single dramatic event, but a slow, relentless degradation of biological integrity. Cancer risk increases substantially. Cataracts form in the lenses of the eyes as radiation damages the transparent cells. Cardiovascular tissue sustains injury that may accelerate heart disease. And perhaps most troublingly, the central nervous system suffers damage that manifests as cognitive decline, impaired memory formation, reduced reaction time, and increased susceptibility to neurological disorders. Animal studies exposing rodents to simulated galactic cosmic ray environments have demonstrated measurable cognitive impairment after exposure levels equivalent to what a crew would receive over a few years of unshielded interstellar transit. The crew would not merely face an elevated cancer risk over decades, they would face a progressive erosion of the mental sharpness they need to operate and maintain the most complex machine ever built in an environment where cognitive failure can mean death. Shielding against galactic cosmic rays is far more difficult than shielding against solar radiation. Solar particles are relatively low energy and can be blocked by modest amounts of material. Galactic cosmic rays are far more energetic. They penetrate meters of solid material, and worse, when high-energy particles strike dense shielding materials like metal, they produce secondary radiation showers of neutrons and other particles that can be more biologically damaging than the original cosmic ray. This phenomenon, called secondary particle production, means that simply adding more metal shielding can actually increase the radiation dose inside the ship rather than reducing it. The optimal shielding strategy for galactic cosmic rays involves using hydrogen-rich materials like water or polyethylene, which absorb incoming particles without generating as many dangerous secondaries. But effective shielding requires substantial thickness, on the order of several meters of water-equivalent material surrounding the entire habitable volume. The mass penalty is enormous, adding thousands of metric tons to a vessel that is already struggling against the tyranny of the rocket equation. Some mission concepts propose generating artificial magnetic fields around the spacecraft to deflect charged particles, mimicking the Earth's magnetosphere. These magnetic shield concepts are theoretically attractive, but engineering nightmares. Generating a magnetic field strong enough to deflect galactic cosmic rays over a volume large enough to protect a crewed habitat requires superconducting magnets of extraordinary size and power, maintained at cryogenic temperatures for decades. The engineering has never been demonstrated at anything approaching the required scale. Other proposals suggest using the ship's fuel supply as shielding during transit, positioning fuel tanks around the habitable areas. This is clever, but only works while fuel remains, and it complicates vehicle design by intertwining propulsion and radiation protection systems. Radiation is not the only hazard in the interstellar medium. The space between stars is not perfectly empty. It contains a sparse but measurable density of hydrogen atoms, roughly 1 atom per cubic centimeter in the local interstellar medium near our solar system. It also contains microscopic dust grains, typically measuring fractions of a micrometer, composed of silicates, carbon compounds, and ices. At low velocities, these particles are harmless. At interstellar cruise speeds, they become weapons. The kinetic energy of an impact scales with the square of the velocity. A dust grain weighing 1 microgram, far smaller than a grain of sand, striking a spacecraft at 10% of the speed of light, delivers kinetic energy equivalent to roughly 450 kilojoules. That is comparable to the kinetic energy of a small car slamming into a wall at highway speed. a single microscopic particle hitting with the force of a vehicle collision. And the ship does not encounter one particle. It encounters a continuous stream over years or decades of transit. Each impact erodes shielding, degrades surfaces, and risks penetrating critical systems. The cumulative effect of billions of such impacts over a 20-year journey at 10% of light speed could be structurally catastrophic. At 20% of light speed, the energy per impact quadruples. A Breakthrough Starshot probe, massing only grams, might tolerate some level of erosion over its brief transit. A crewed vessel, which must arrive intact and functional, faces a far more severe challenge. The ship's forward-facing surfaces must withstand a sustained bombardment that no terrestrial material has been tested against at these velocities. Designing a hull that survives this requires material science that does not currently exist, validated through testing regimes that have never been attempted. And then there is the question of mechanical endurance over timescales that no human machine has ever been asked to tolerate. The Voyager spacecraft, the longest operating deep space machines in history, illustrate the problem with painful clarity. As of 2026, both Voyagers are approaching 50 years of continuous operation. They have been engineering marvels, but they are failing. Voyager 1 now operates with only 2 scientific instruments still active. Heaters have been turned off, backup systems have been exhausted, thruster lines are clogging. In October 2024, a fault protection event shut down Voyager 1's primary X-band transmitter, temporarily reverting communication to its backup S-band system, last used in 1981. Engineers managed to restore the X-band link after weeks of troubleshooting across a signal delay approaching 23 hours each way. Between May 2025 and February 2026, the only antenna on Earth capable of sending commands to Voyager, Deep Space Station 43 in Canberra, Australia, was offline for repairs, leaving both Voyagers unable to receive instructions for months. 50 years. 2 instruments. Clogging thrusters. Failing transmitters. Single-string systems with no remaining backups. And these are spacecraft that carry no crew, require no life support, operate no moving mechanical systems beyond thrusters and scan platforms, and weigh less than a metric ton each. A crewed interstellar vessel would be orders of magnitude more complex. It would contain atmospheric processing systems, water recycling plants, food production facilities, thermal regulation systems, power generation and distribution networks, waste management systems, medical equipment, communication arrays, navigation computers, propulsion systems, structural monitoring sensors, and airlocks. Every one of these systems would need to operate without critical failure for the entire duration of the journey. Decades at minimum. A century or more in many scenarios. No human-built system has ever demonstrated that level of reliability. Industrial machinery on Earth is maintained, repaired, and eventually replaced. The components degrade, seals fail, bearings wear, electronics accumulate radiation damage, software encounters unforeseen edge cases, mechanical systems fatigue. The longer any machine operates, the more likely failure becomes, and the failure probability compounds across thousands of interdependent subsystems. The crew could carry spare parts, they could carry manufacturing equipment, they could train as mechanics, electricians, plumbers, doctors, and engineers, but they cannot carry spares for everything, and they cannot anticipate every failure mode. Some components will break in ways no one predicted. Some materials will degrade in ways that only manifest after decades of exposure to the interstellar environment. And when those failures occur, the crew must diagnose and repair them using only what they have, because nothing else will ever arrive. The ship is not a vehicle, it is a closed world, and closed worlds that cannot be resupplied are subject to a brutal principle. Entropy wins eventually, and the only question is whether the inhabitants can delay that victory long enough to reach their destination. This brings the journey to its most intimate and perhaps most devastating dimension, the human mind. Space psychology is a mature field built on decades of research into how humans respond to confinement, isolation, monotony, danger, and separation from familiar environments. The data is consistent and sobering. Even short-duration space missions produce measurable psychological effects. Astronauts on 6-month International Space Station increments report sleep disruption, interpersonal tension, cognitive fatigue, and periods of low mood. Longer simulation studies, such as the Mars 500 experiment conducted in Moscow between 2010 and 2011, confined 6 volunteers in a sealed habitat for 520 days to simulate a round-trip Mars mission. Participants experienced depression, social withdrawal, disrupted sleep-wake cycles, and increasing interpersonal conflict as the months wore on. One crew member became so sedentary and withdrawn that researchers classified his behavior pattern as consistent with chronic depression. These effects emerged in a simulation where participants knew they were on Earth, knew they could quit if necessary, and knew the experiment would end. An interstellar crew would have none of those psychological safety nets. They would not be simulating a journey. They would be on one, with no exit and no endpoint visible from the present. The destination would be years or decades away. Earth would be a signal source growing fainter and more delayed with every passing month. The daily environment would consist of the same corridors, the same faces, the same recycled air, the same artificial lighting, the same routines, repeated thousands of times without variation. There would be no new landscapes, no changing seasons, no strangers to meet, no fresh food from an unfamiliar restaurant, no rain on the skin, no wind, no horizon beyond the hull. Consider what the sensory environment actually consists of. The lighting would be artificial, calibrated to approximate a diurnal cycle but never varying the way natural light does, never the golden angle of late afternoon, never the grey diffusion of an overcast morning, never the slow deepening of a winter dusk. The air would be recycled, scrubbed, mechanically humidified, always carrying the faint scent of filtration systems and polymer outgassing. The sounds would be the hum of air handlers, the vibration of structural elements under thrust, the clicks and whirs of mechanical systems in their endless maintenance cycles. Gravity, if the ship rotates to produce artificial gravity, would feel subtly wrong. The Coriolis effect would make dropped objects curve. Walking in one direction would feel slightly different from walking in the other, and the inner ear would register discrepancies that the brain could never fully adapt to. If the ship does not rotate, the crew lives in microgravity, with all of its attendant health consequences: bone density loss, muscle atrophy, fluid redistribution toward the head, vision impairment from intracranial pressure changes. Either option produces a physical environment that is tolerable for months, but corrosive over years. The biological environment would be equally impoverished. No animals beyond whatever the life support system requires. No birdsong, no insects, no rustling of leaves, no bodies of water large enough to swim in or even sit beside. The food, however carefully cultivated in onboard hydroponic systems, would lack the variety that a planet's ecosystem provides. No wild-caught fish, no orchard fruit, no bread from a neighborhood bakery. The menu would cycle through whatever the food production modules could sustain, and over years, the repetition would flatten the experience of eating from a source of pleasure into a mechanical necessity. These deprivations sound minor in isolation. No one dies from the absence of birdsong. But sensory richness is not a luxury. It is a substrate on which human cognition operates. The brain requires varied input to maintain flexibility, creativity, alertness, and emotional regulation. Studies of sensory deprivation in controlled settings show measurable cognitive decline within days, reduced attention, impaired problem-solving, increased susceptibility to hallucination, and emotional instability. An interstellar mission does not produce total sensory deprivation, but it produces a form of sensory monotony so complete and so unbroken that its effects over years or decades have no precedent in human experience. Human beings are not built for this. Our cognitive and emotional systems evolved in environments rich with novelty, social complexity, natural cycles of light and dark, seasonal variation, and unpredictable stimuli. Strip all of that away and confine a person in a sealed environment for years, and the psychological consequences are severe and well documented in analogous settings. Submarine crews, Antarctic winter-over personnel, and long-duration space station residents all report versions of the same syndrome: irritability, cognitive dulling, emotional flatness, social withdrawal, disrupted sleep, and a pervasive sense of meaninglessness that researchers have termed the third quarter phenomenon, a motivational collapse that typically occurs roughly 3/4 of the way through any extended confinement period. On an interstellar mission lasting decades, the third quarter phenomenon would not be a phase. It would be a recurring wave, cresting and receding as the crew moves through the interminable middle passage of a journey with no landmarks and no milestones beyond the ticking of instruments measuring distance yet to cover. Interpersonal dynamics compound the problem. Small groups confined together for long periods develop friction with statistical certainty. Personality clashes, power struggles, romantic entanglements, grudges, and communication breakdowns emerge in every long-duration confinement study ever conducted. On a submarine, a tour lasts months and the crew rotates. On an interstellar vessel, the crew is permanent. There is no transfer, no reassignment, no shore leave, no new personnel to disrupt entrenched social patterns. If two crew members develop an irreconcilable conflict, they must continue living and working within meters of each other for the remainder of their lives. If a leader becomes unstable or authoritarian, there is no higher authority to intervene. The ship's social structure must be self-correcting, or it must endure dysfunction, because no external force can mediate, replace, or remove anyone. The psychological burden extends to the mission's fundamental meaning. Exploration has always drawn its motivation from the promise of return. Explorers leave home, discover something, and come back to share what they found. The return is what transforms endurance into story, suffering into achievement, distance into knowledge that benefits the civilization left behind. An interstellar crew that departs for Proxima Centauri on a journey lasting decades may never return. Even if the technology exists to make the trip, the return voyage doubles the time. A 40-year outbound journey becomes an 80-year round trip. The crew members who departed as young adults arrive back on Earth as elderly survivors in a world that has changed beyond recognition, if they survive at all. More likely, the mission is one way. The crew leaves knowing they will never see Earth again. They leave knowing their families will age and die while light-speed messages crawl across the void. They leave knowing that the world they remember will not be the world that exists when their messages arrive. They are not explorers in any traditional sense. They are emigrants. They are exiles. And the emotional weight of voluntary, permanent, irrevocable exile from everything familiar is a burden that no selection process, no training program, and no onboard therapy system has been designed to manage, because no human being has ever had to carry it. Each of these challenges, communication delay, rescue impossibility, radiation exposure, mechanical fragility, and psychological endurance, is independently severe enough to threaten any interstellar mission. Taken individually, each one represents a problem at or beyond the current frontier of human engineering and human psychology. But they do not occur individually. They occur simultaneously, compounding each other in ways that multiply the total risk far beyond the sum of the parts. Consider how these failures cascade in practice. A galactic cosmic ray heavy ion event damages a circuit board in the atmospheric processing system. The system does not fail immediately. It begins producing slightly elevated carbon dioxide levels, not enough to trigger an alarm, but enough to cause headaches, impaired concentration, and disrupted sleep over weeks. The crew, already experiencing the cognitive dulling of long-duration confinement, does not identify the problem quickly. By the time the fault is diagnosed, the degraded air quality has affected decision-making aboard the ship, and the repair requires a component that was manufactured on Earth and cannot be perfectly replicated with onboard fabrication tools. The crew improvises a workaround using materials from a backup system designed for a different purpose. That workaround weakens the backup system's capacity to respond to a future failure. The margin shrinks. The next failure starts from a weaker position. Or, consider a different cascade. A dust grain impact at relativistic speed penetrates the outermost layer of hull shielding and damages a coolant line in the thermal regulation system. The leak is slow but persistent. Thermal management begins to fail in one section of the habitat. The crew relocates, crowding into a smaller area while repairs are attempted. The crowding intensifies interpersonal friction that has been building for years. A conflict between two crew members escalates during the repair operation, delaying the fix. The thermal imbalance affects the food production module, which loses a crop cycle. The food supply tightens, rationing begins, morale drops. The next system failure occurs in an environment where the crew is already hungry, crowded, sleep-deprived, and at each other's throats. No single event in this chain is catastrophic. Each is manageable in isolation, but they do not occur in isolation. They compound, each degradation making the next one harder to survive, each repair consuming resources that cannot be replaced, each interpersonal fracture widening under the pressure of continuous confinement with no relief. This compounding is not speculative. It is the documented behavior of complex systems operating under stress without external resupply. It is the reason submarines rotate crews. It is the reason Antarctic stations receive resupply flights. It is the reason the International Space Station receives cargo missions every few weeks. Every long-duration human operation in a hostile environment has learned, through hard experience, that isolated systems degrade and that degradation compounds. An interstellar vessel would be the first human habitat to operate under these compounding pressures for decades without any external input. The margin for error is not thin. It is a knife edge sustained over a time span longer than most nations have survived. The void between stars is not merely empty space. It is an environment of compounding hostility, where distance, time, radiation, particle bombardment, mechanical entropy, and psychological degradation converge into a single, sustained assault on everything a crewed mission requires to survive. The journey to Proxima Centauri does not merely test technology. It tests the entire concept of human self-sufficiency. In a setting where self-sufficiency is the only option and the margin for error is measured in the difference between survival and extinction. And here, at the edge of endurance, is where the final and deepest layer of the journey reveals itself. Because everything described so far, the isolation, the fragility, the compounding risk, describes the physical and psychological burden of crossing the void. But the journey to Proxima Centauri carries one more weight. A weight that is not mechanical or biological but temporal. The journey does not just separate travelers from Earth in space, it separates them in time. And that separation changes the meaning of the journey itself in ways that the crew cannot anticipate, the mission planners cannot control, and the human mind may not be equipped to bear. Time is the cruelest dimension of the journey to Proxima Centauri. Distance can be measured and, in principle, divided. Speed can be increased, at least in theory, through better propulsion. Isolation can be mitigated, at least partially, through onboard community and routine. But time cannot be compressed, negotiated, or outrun. It passes at the same rate inside the ship as it does on the Earth left behind, with one narrow and deeply strange exception that makes the problem not simpler but stranger. And the way time operates across interstellar distances transforms the journey from a voyage into something that has no precedent in the history of human experience. Something closer to a departure from the human timeline itself. Start with the most straightforward version of the problem. If a crewed vessel departs Earth for Proxima Centauri at 5% of the speed of light, a velocity that requires fusion propulsion systems that do not yet exist, the journey takes approximately 84 years. The crew members who board the ship at age 30 will be 114 years old when it arrives. They will almost certainly be dead. Their children, born during the first decade of transit, might survive to see arrival in their 70s or 80s. But the people who made the decision to go, the people who trained for the mission, who said goodbye to their families, who watched Earth shrink to a point of light indistinguishable from the stars, Those people will never reach the destination. They will live out their entire remaining lives inside the vessel. They will grow old in corridors they have walked 10,000 times. They will die surrounded by the hum of recycled air and the faint vibration of engines pushing against the void. And their deaths will not end the mission. They will simply pass the burden to the next generation. This is the generation ship concept, and it is the only crude interstellar architecture that does not require propulsion breakthroughs bordering on the miraculous. If you cannot make the journey fast enough for one crew to survive it, you design a vessel large enough to sustain a self-reproducing human population across multiple generations. The ship becomes not a vehicle but a habitat, a world, a sealed civilization traveling through darkness for decades or centuries, populated by people who were born aboard, who will live their entire lives aboard, and who will die aboard, carrying forward a mission that was chosen for them by ancestors they will never meet. The ethical weight of this concept is staggering. The first generation, the founders, board voluntarily. They understand the commitment. They accept the sacrifice. But their children do not choose. Their grandchildren do not choose. Every subsequent generation inherits a destiny imposed by people who are already dead. These descendants are born into confinement. They grow up knowing that the walls around them are the walls of a ship, that the sky they have never seen is a concept described in databases, that the earth their great-grandparents left behind is a place they will never visit, never touch, never breathe the air of. Their entire existence is defined by a journey they did not start, aimed at a destination they have only been told about, justified by a purpose they must accept on faith, because no one alive has any direct experience of the world that launched the mission. This raises questions that engineering cannot answer. Is it ethical to create human lives whose sole context is transit? Is it acceptable to bring children into existence inside a sealed vessel knowing they will never experience an open sky, a natural ecosystem, a body of water larger than a reservoir tank, the warmth of an unfiltered sun? The founders might argue that the destination justifies the sacrifice, that the generations born in transit are paying a price for a future that their descendants will inherit. But the intermediate generations, the ones born too late to remember Earth and too early to see Proxima Centauri, receive neither the memory of departure nor the reward of arrival. They live entirely within the journey. The journey is their whole world, and they did not consent to it. Consider what daily life looks like for a person born in the 4th generation of a 10-generation voyage. This person has never seen Earth. Their grandparents never saw Earth. The founding generation exists only as names in a historical archive, faces in recordings, voices explaining a decision made over a century ago. The destination, Proxima Centauri, is still 6 generations away. It is not a place this person will ever reach. It is not a place anyone they know will ever reach. The entire arc of their life, from birth to education to work to reproduction to aging to death, will unfold inside the same vessel. Their career will consist of maintaining systems that keep the ship functional for a journey whose purpose they inherited and whose completion they will never witness. Their social world consists of the same few hundred or few thousand people they have known since childhood, and will know until they die. Their children will be born into the same world and face the same constraints. The journey is not a temporary condition that defines a period of their life. It is the totality of their existence. They are not travellers. They are inhabitants of a machine whose only function is to continue moving through a void that none of them chose to enter. What motivates such a person to maintain the ship? To reproduce? To educate the next generation? To preserve knowledge and capability that will only matter 6 generations hence? These are not engineering questions. They are questions about the limits of inherited purpose, about whether human beings can sustain commitment to a goal they will never see achieved, about whether meaning can survive transmission across centuries of confinement without mutating into something unrecognizable. No human society has ever tested these questions under conditions of total isolation and permanent enclosure. We have no data. We have only the grim historical record of isolated communities that lost coherence, purpose, and knowledge within a handful of generations, even when they were not sealed inside a metal shell flying through nothingness. Some theorists have proposed that generation ships could develop their own cultures, their own traditions, their own sense of meaning independent of the original mission. Perhaps the shipboard community would come to see the vessel itself as home rather than as a vehicle. Perhaps the journey would become the point rather than the destination. This is an optimistic reading, and it may have some psychological validity. Humans are remarkably adaptive. Communities form in prisons, on oil rigs, in submarine fleets, in Antarctic stations. People create meaning in constrained environments because creating meaning is what human cognition does under pressure. But every analogy breaks down at the interstellar scale. Prison sentences end. Oil rig rotations cycle. Submarine tours conclude. Antarctic winters give way to resupply flights. The generation ship never docks. The generation ship never opens its doors to a familiar world. The constrained environment is permanent for every person born within it, and the psychological literature on permanent confinement without the possibility of release describes outcomes that are not optimistic. They describe institutionalization, learned helplessness, and the gradual erosion of the cognitive flexibility that makes human beings adaptable in the first place. There is also the question of social stability across centuries. No human institution has survived intact for the timescales a generation ship requires. The Roman Empire in its various forms, the papacy, certain Chinese dynasties each lasted at most a few centuries, before transforming beyond recognition or collapsing entirely. A generation ship must maintain not just mechanical function but social coherence, shared purpose, and knowledge continuity for periods exceeding the lifespan of any civilization in recorded history. The ship's governance must survive leadership transitions, ideological shifts, interpersonal feuds, resource disputes, and the inevitable drift of cultural values across generations. It must do all of this in a closed environment, with no external pressure to force cooperation, no outside threat to unify against, and no frontier to expand into. The only frontier is arrival, and for most of the journey, arrival is an abstraction too distant to motivate daily sacrifice. History suggests that isolated communities cut off from the larger world undergo rapid cultural drift. Island populations develop distinct languages, customs, and belief systems within a few generations. Religious communities that seal themselves from outside influence produce doctrines and practices that diverge dramatically from their founding principles. A generation ship would be the most isolated community in the history of the species, sealed inside a metal shell with no contact beyond time-delayed messages from an Earth that grows more alien with every passing year. The culture aboard the ship after 10 generations might bear little resemblance to the culture that launched it. The mission's original purpose might be reinterpreted, questioned, rejected, or forgotten. The knowledge required to operate the ship's systems might degrade as educational priorities shift across generations. The skills needed to land, establish a settlement, and survive on an alien world might atrophy during centuries of transit when those skills have no practical application. This is the temporal trap of the generation ship. It must sustain purpose, knowledge, cohesion, and capability across timescales that no human society has ever maintained any of these things. And it must do so inside a sealed container with no margin for social collapse, because social collapse aboard a generation ship is not a political setback, it is an extinction event. Now consider the one phenomenon that seems to offer an escape from the tyranny of time: relativistic time dilation. Einstein's special theory of relativity, confirmed by a century of experimental evidence, predicts that time passes more slowly for objects moving at significant fractions of the speed of light relative to a stationary observer. This is not an illusion. It is not a measurement artifact. It is a fundamental property of space-time itself. A clock aboard a spacecraft travelling at high velocity ticks more slowly than a clock on Earth. The crew ages less than the people they left behind. At 50% of the speed of light, the dilation factor is modest. Time aboard the ship passes at roughly 87% of the rate on Earth. A journey that takes 8.48 years as measured from Earth would feel like approximately 7.3 years to the crew. Noticeable, but not transformative. At 90% of the speed of light, the dilation becomes dramatic. Time aboard the ship passes at roughly 44% of the Earth rate. The crew would experience the 4.24 light-year journey in approximately 2 years of shipboard time, while roughly 4.7 years would elapse on Earth. At 99% of the speed of light, the dilation factor reaches approximately 7. The crew would experience the journey in roughly 7 months of subjective time, while over 4 years passed on Earth. These numbers seem like salvation. If you could accelerate a crewed vessel to 90% of the speed of light, the crew would arrive at Proxima Centauri having aged only about 2 years. The journey would be shorter than many submarine deployments. The psychological burden would be manageable. The mechanical endurance requirements would be modest. Time dilation appears to solve the cruelest aspects of interstellar travel in a single, elegant stroke of physics. But the elegance is a mirage. The energy required to accelerate a crewed vessel to 90% of the speed of light is almost incomprehensibly vast. As an object with mass approaches the speed of light, its relativistic mass increases, meaning each additional unit of velocity requires more energy than the last. The relationship is not linear, it is asymptotic. Reaching 90% of light speed requires accelerating the ship's rest mass to a kinetic energy roughly equal to its total mass energy equivalent, multiplied by a factor of 1.3. For a vessel weighing 1,000 metric tons, a modest size for a crewed interstellar ship, the kinetic energy at 90% of light speed would be approximately 1.17 times 10 to the 23rd joules. That is roughly equivalent to the total energy consumption of human civilization over 200 years, compressed into the kinetic energy of a single vessel. For one ship, the energy budget is not merely beyond current technology, it is beyond any energy source humanity has seriously proposed for spaceflight. Even antimatter, the most energy-dense fuel conceivable under known physics, would require hundreds of metric tons to accelerate and then decelerate a crewed vessel at these velocities, and humanity currently produces antimatter in quantities measured in nanograms per year at costs of trillions of dollars per gram. At more plausible velocities, 10 to 20% of the speed of light, time dilation is negligible. At 10% of light speed, time aboard the ship passes at roughly 99.5% of the Earth rate. The crew saves less than 6 months over a 42-year journey. The dilation is real but irrelevant to the human experience of the trip. The journey still takes decades. The crew still ages. The generations still turn over if the voyage is long enough. Time dilation does not help at the speeds humanity might actually achieve. It only helps at speeds that require energy budgets indistinguishable from fantasy. And even in the hypothetical scenario where relativistic velocities are achieved, time dilation creates a new and deeply unsettling problem. It does not eliminate the time that passes on Earth. It only compresses the time that passes on the ship. A crew that experiences 2 years of travel at 90% of light speed arrives at Proxima Centauri to find that nearly 5 years have passed on Earth. If they somehow make the return journey at the same speed, they come home to an Earth that has aged roughly a decade since their departure, while they themselves have aged only about 4. The gap sounds modest for a single trip to the nearest star, but it scales with distance. A journey to a star 20 light-years away at 90% of light speed produces a round-trip displacement of nearly 45 years on Earth versus roughly 19 years aboard. The crew returns to find a world that has moved on by nearly half a century. Friends have retired, children have grown up and grown old. The world has changed in ways that no amount of time-delayed correspondence could have prepared the travellers for. The returning crew members are temporal refugees, displaced not in space but in time, arriving in a present that is no longer theirs. This temporal displacement has been explored extensively in thought experiments and fiction, but its psychological reality is devastating. Even at the nearest star, the effect is measurable. A few years lost to dilation compounds across distance. But the true horror emerges at greater range. A crew member who departs at age 30 for a star 40 light-years away at 99% of light speed returns at roughly age 41. On Earth, more than 80 years have passed. Everyone the traveller knew is dead. The civilization that launched the mission has transformed beyond recognition. The relationships that defined the crew member's identity before departure have not merely changed, they have ended. The homecoming is not a reunion. It is an arrival into a world that remembers the traveller only as a historical figure from a previous era. At extreme velocities, the displacement compounds grotesquely. A hypothetical crew travelling at 99.9% of the speed of light to a star 100 light-years away would experience the journey in roughly 4.5 years of shipboard time, while over 100 years elapsed on Earth. They would return to a planet where their language had drifted into an unfamiliar dialect, where the political borders they memorized no longer existed, where the institutions that trained and launched them had been dissolved, rebuilt, and dissolved again. Not merely a world that had moved on, but a world that had forgotten why the mission mattered and then remembered, and then forgotten again, several times over, in the century since departure. The travellers would step off the ship biologically young and find themselves artifacts, curiosities from an age as distant to their descendants as the Victorian era is to us. Time dilation does not conquer time. It weaponizes it. It allows the crew to survive the journey, but strips them of the temporal context that makes survival meaningful. They arrive in the future, but belong to the past. This is the temporal dimension of interstellar travel that no engineering solution addresses. The journey to Proxima Centauri, regardless of how it is conducted, severs the travellers from their own time. At slow speeds, the separation is generational. The founders die in transit, and their descendants arrive as strangers to both worlds, the Earth they never saw and the Proxima system they were born to reach. At fast speeds, the separation is relativistic. The crew arrives biologically young but temporally displaced, out of sync with the civilization that sent them. At any speed, the journey creates a rupture between the travellers and the human timeline they departed from. They do not merely leave Earth, they leave the present, and the present, unlike a location, cannot be returned to. This rupture is the deepest source of terror in the journey to Proxima Centauri. Not the distance, not the speed, not the radiation or the dust, or the mechanical fragility or the psychological strain. Those are problems that can, in theory, be engineered around given sufficient technology, sufficient resources, sufficient ingenuity. The temporal rupture cannot be engineered around. It is a consequence of the speed of light, the distances between stars, and the way time flows for objects separated by light years. No technology can make the journey instantaneous. No propulsion system can eliminate the delay. No communication system can make a conversation across 4.24 light-years feel like a phone call. The speed of light is not a technical barrier waiting to be broken. It is a law of physics, as fundamental as the conservation of energy or the increase of entropy. It defines the universe, and what it defines at interstellar distances is separation. Permanent, irreversible, structural separation between the travellers and everything they leave behind. This is what the title means. The terrifying journey to Proxima Centauri is not terrifying because Proxima Centauri is exotic or hostile or mysterious. The star itself is a dim, quiet red dwarf with a small retinue of battered planets. The terrifying part is that Proxima Centauri is the nearest star, the closest possible interstellar destination, the least extreme version of the problem. And even this least extreme version demands a journey so long, so isolating, so severed from Earth and from the human timeline, that it stops resembling exploration and begins resembling something else entirely. A departure, not from a planet, from the human world itself. Every previous act of exploration in human history maintained a connection to the world the explorers left behind. Columbus sailed west and returned east. Magellan's expeditions circumnavigated the globe. Apollo astronauts walked on the moon and came home 3 days later. Even the most extreme polar expeditions, the most dangerous mountaineering ascents, the deepest ocean dives, preserved some thread of continuity between the explorer and the civilization that produced them. The explorer left, experienced something extraordinary, and returned to share it. The departure was temporary, the distance was reversible, the time away was bounded. An interstellar journey breaks every one of these threads. The departure is permanent or near permanent. The distance is reversible, only at costs measured in decades or lifetimes. The time away is so vast that the world the travellers left behind will not be the world that exists when their messages arrive, let alone when they might hypothetically return. The journey does not extend human reach. It exceeds it. It pushes past the boundary of what human beings can do, while remaining connected to the species, the culture, the history, and the time that produced them. The travellers become something new, not explorers, not colonists, at least not in any sense that previous colonists would recognise. They become the first humans to exist outside the temporal and spatial framework that has defined every human life ever lived. And this is only the nearest star. This is the mildest version of the problem. If Proxima Centauri at 4.2, 4 light-years already demands multi-generational journeys, relativistic velocities, permanent exile, and total severance from Earth's timeline, what does the rest of the galaxy demand? The Milky Way contains roughly 400 billion stars. The nearest few dozen are within 20 light-years. The nearest few thousand are within 100 light-years. The galaxy itself spans 100,000 light-years or more. The journey to Proxima Centauri is not the first rung on a ladder that humanity can climb star by star toward galactic civilization. It is a demonstration that the ladder itself may not exist, that the distances between stars are not challenges to be overcome, but boundaries to be respected, that the galaxy is not a neighbourhood waiting to be explored, but a vast archipelago of isolated islands separated by oceans so wide that crossing even the narrowest channel requires abandoning almost everything that makes the crossing meaningful. The universe does not forbid interstellar travel. Physics allows it. Objects can cross interstellar distances. Voyager 1 is doing it right now, slowly, silently, carrying a golden record inscribed with sounds and images from a planet it will never see again. But the universe prices interstellar travel at a rate that human beings may not be able to pay, not in dollars, not in engineering hours, in time, in connection, in the continuity between who you are when you leave and who you become when you arrive. The cost of reaching the nearest star is not merely the fuel, the technology, the shielding and the life support. The cost is the surrender of everything that ties the travellers to the world that built the ship. Proxima Centauri sits 4.24 light-years away, a dim red dwarf circled by a handful of small battered worlds, one of which might, under the right conditions, harbour liquid water on its surface. It is the nearest star, the closest destination beyond our solar system, the most accessible point in the entire galaxy, and reaching it would require a journey so extreme in duration, so absolute in isolation, so total in its severance from Earth and from the present, that the people who undertake it would no longer be travellers in any sense our species has ever known. They would be something else, pioneers of a kind that has no precedent, exiles who chose exile, humans who left the human world behind, not because the destination demanded it, but because the space between here and there demanded it, because the void demanded it. Because 4.2, 4 light-years of nothing, the shortest interstellar distance in the sky, is already enough to transform travel into departure, exploration into exile, and the promise of the stars into a burden so heavy that the nearest one already feels like too far. The terrifying journey to Proxima Centauri is not terrifying because of what waits at the destination. It is terrifying because of what the journey requires you to leave behind. And the most unsettling truth is that this is the closest star. This is the easiest case. This is the shortest crossing the galaxy offers. Everything beyond is farther, longer, harder, more isolating, more demanding of a sacrifice that already, at 4.24 light-years, feels like more than humanity was built to give. The stars are right there. You can see them every night. They look so close. They have always looked close. And the nearest one, the very nearest, is already impossibly, terrifyingly, beautifully far.